What if I told you that reality itself changes the moment you look at it? Not in a metaphorical sense, but in the literal fabric of existence. What if just the act of watching, of being present, of noticing, was enough to shift the outcome of events? This isn't science fiction. This isn't a story from a movie. This is the mystery at the heart of one of the most mind-bending discoveries in physics: the observer effect. Imagine a universe where particles behave like waves, flowing freely, with infinite possibilities. But the instant someone observes them, they collapse into a single outcome. It's as if the universe waits for your attention before deciding what's real. That is not only bizarre, it is revolutionary. Because if observation shapes reality, then your role in this universe is far greater than you've been taught. In this video, we are going to dive into why the observer effect changes everything. We'll go beyond the surface, past the familiar buzzwords, into insights most people never hear. You'll discover how observation doesn't just disturb tiny particles, but challenges the way we think about science, consciousness, and even the choices we make every single day. Consider this: when researchers first ran the famous double-slit experiment, they expected particles to act in predictable ways. But the outcome shocked the world. Left alone, particles created patterns of waves, spreading into endless potential. Observed, they snapped into neat solid paths, as if they knew they were being watched. It was as if the universe itself cared about the observer. That one discovery forced us to rethink what we mean by reality. But here's where the suspense deepens. The observer effect doesn't belong only in laboratories. You experience it every day, without realizing. Ever notice how people behave differently when they know they're being watched? That's the observer effect in action. Even in technology, when engineers try to measure a system, their very tools change its performance. Everywhere you look, observation is not passive, it's active, it's powerful. And that brings us to the deeper question: who or what is the observer? Is it human consciousness? Is it a measuring device? Or is it something even larger, something woven into the fabric of the cosmos? Physicists and philosophers have wrestled with this for decades. Some say the act of consciousness is the key. Others argue it's simply interaction, not awareness. Yet the mystery remains. The universe seems unfinished until it is observed. Now here's the part no one tells you. The observer effect is not just a scientific curiosity, it's a mirror for your life. How many possibilities are waiting in your reality? Waves of potential that collapse into form only when you give them attention. What you choose to look at, what you choose to focus on, becomes solid, becomes real. Your attention is not neutral, it's creative. Stay with me until the end of this video, because once you truly grasp the observer effect, you will never see your role in the universe the same way again. What you'll learn here will challenge how you view science, reality, and even yourself. And it might just make you realize that by watching, by focusing, you are already shaping the world around you. Before we talk about the strange mysteries of the quantum world, let's start with something simple. Think about checking the air pressure in your car tire. The moment you attach a gauge to measure it, a little bit of air escapes. By observing, you've already changed what you were trying to measure. That's the observer effect in its most basic form. It happens in many areas of life. When you measure the temperature of water, the thermometer draws in some of the heat. When a researcher studies human behavior, the subjects act differently because they know someone is watching. In the classical world, observation always comes with some level of disturbance. Now in everyday situations like these, the effect feels small. The tire doesn't suddenly vanish because you looked at it. The temperature doesn't completely shift just because of the thermometer. Observation in classical science is about disturbance. You measure, you interact, and that interaction nudges the system a little. It's like dipping your hand in a pond to test the water. Your hand creates ripples, but the pond remains. This is what most of us expect from the act of observing, a small influence, nothing dramatic. But then comes the quantum world, where the rules are completely different. At the smallest levels of reality, atoms, electrons, photons, observation does more than disturb. It changes the very nature of what is being observed. A particle isn't just a particle waiting for you to find it. It exists as a wave of probabilities, spread out, holding countless possibilities all at once. But the moment it is observed, it collapses into one definite state. It stops being a wave of maybes and becomes a solid, this or that. Observation doesn't just nudge, it defines. This is what makes quantum observation so shocking. In classical physics, the ball is rolling down the hill, whether or not you watch it. In quantum physics, the ball doesn't even choose a path until you look. The universe seems to withhold its decision until the observer steps in. That's why experiments like the double-slit experiment left scientists stunned. Particles acted like waves when no one was looking, but the moment someone tried to detect which path they took, they acted like particles. The act of observing forced them to make a choice. This is not the kind of disturbance you see with a tire gauge or a thermometer. It's not just interference, it's transformation. Observation turns a cloud of possibilities into a single outcome. Without observation, the system stays in superposition, existing in all states at once. With observation, reality locks into one version of itself. It's as if reality refuses to settle until someone is there to witness it. That's why the difference between classical and quantum observation is so profound. One is about influence, the other is about existence. In the classical world, observation changes details. In the quantum world, observation decides reality, and once you see that difference, the role of the observer no longer feels ordinary. It becomes a mystery that sits at the heart of existence itself. When people hear about the observer effect, they often think it only belongs to the strange world of quantum physics. But the truth is, you've experienced it in the ordinary, physical world many times without even realizing it. In fact, observer effects are everywhere, and they show up in simple situations you probably deal with in your daily life. Take something as basic as checking the air in a tire. You want to measure the pressure, so you connect a gauge, but in the very act of attaching the device, a little bit of air escapes. The reading you get is close, but it isn't perfectly what it was before you started measuring. The act of checking has already changed the thing you were trying to check. That's the observer effect in action, direct, obvious, and something most people overlook. The same thing happens in electronics. Engineers know that when they try to measure what's happening in a circuit, the very instruments they use can disturb the signal. Plugging in a probe or a meter adds extra resistance, capacitance or load to the system. Suddenly the circuit isn't exactly the same as it was before. You get a result, but the act of measuring changed the reality you were hoping to capture. The more sensitive the system, the more noticeable the effect becomes. That's why electronics experts design special tools to be as invisible as possible, but no tool can ever be perfectly invisible. Measurement always leaves a fingerprint. This doesn't only happen in machines or physical systems, it happens in people too. Think about being in a room where you know someone is watching you. You sit differently, speak differently, behave differently. You might try harder, or you might act more cautious. In psychology, this is often called the Hawthorne effect. People in studies change their performance or behavior simply because they are being observed. They don't have to be told to act differently. The awareness of being watched is enough to alter the outcome. What's fascinating is that this pattern shows up across disciplines. In physics, in engineering, in social science, the observer is never neutral. You can't study something without leaving some trace on it. You can't measure without changing. That's exactly what researcher Kenneth Bucklowski pointed out. Observer effects exist even in classical systems, not just in quantum mysteries. Whether it's air in a tire, current in a circuit, or people in an experiment, the principle is the same. Observation is interaction. Observation is participation. This makes you realize that even in the most familiar parts of life, the line between watching and changing is thinner than you think. Every time we step in to measure, test, or even notice, the system responds. Sometimes the effect is small, almost invisible. Sometimes it's large and obvious, but it's always there, quietly reminding us that the role of the observer is never as passive as it seems. In the quantum world, the act of observation doesn't just disturb what is being measured, it goes much deeper. It forces particles to make a choice. Before observation, they exist in a strange state of possibilities. After observation, they collapse into one clear outcome. This isn't like checking tire pressure or testing a circuit. This is reality itself shifting, depending on whether or not someone is watching. The double-slit experiment is the clearest example of this. When particles such as electrons or photons are fired toward a barrier with two slits, you'd expect them to form two neat bands on the screen behind it, like little bullets passing through one slit or the other. But when no one measures their path, something entirely different happens. The particles spread out as waves, interfering with each other, and create a pattern of stripes, like ripples on water. They don't act like individual particles at all, they act like a field of possibilities. Now here's the twist. The moment scientists try to observe which slit the particles pass through, the pattern changes, the interference disappears, and the particles suddenly behave like solid bullets, leaving two clear clusters behind the slits. It's as if the particles knew they were being observed and decided to act differently. This shift from wave to particle, from possibilities to one outcome, is what physicists call wave function collapse. The wave function is a mathematical description of all the possible states a particle can exist in. Before observation, the particle is not in one place or another, it exists in a cloud of potential, a spread of probabilities. Observation forces that cloud to collapse into one definite reality. Out of all the possibilities, only one survives, and the rest vanish. The act of looking doesn't just reveal what was already there, it decides what becomes real. This strange effect connects closely with Heisenberg's uncertainty principle. According to this principle, there are limits to what you can know about a quantum particle. You can measure its position, or you can measure its momentum, but never both with perfect precision. The more accurately you observe one property, the less accurately you can know the other. This isn't a problem with our tools, it's a fundamental feature of nature itself. Measurement always comes with trade-offs, and observation always changes the system in some way. Together, wave function collapse and the uncertainty principle show us a universe that doesn't behave like the solid, predictable world we see around us. At the quantum level, reality is flexible, undefined, and filled with potential until someone interacts with it. The observer doesn't just peek into reality, the observer shapes it, decides it, locks it into form. The universe, it seems, is not fully committed to an outcome until an observation takes place, and that simple truth has left physicists and philosophers questioning the very nature of what it means for something to exist. The observer effect challenges one of the oldest assumptions about the universe, that it exists completely independent of us. For centuries, science was built on the idea that reality is out there, fixed, unchanging, waiting to be measured like a machine ticking along. According to that view, humans are just passive spectators, recording what already is. But quantum physics has shaken that belief to its core. The moment we try to observe, the outcome changes. The universe doesn't stand apart from us, it responds to us. This means that our tools are not neutral. The detectors, the gauges, the microscopes, all of them leave a mark. They don't simply reveal reality as it is, they shape it by interacting with it. A particle is not a passive object sitting there, waiting to be photographed. The tools we use to look at it actually change its behavior. Even the design of an experiment reflects choices made by human beings. Whether we set up to measure a particle's position or its momentum, whether we observe the path it takes or ignore it, our choices decide which version of reality comes into view. It goes even deeper than just equipment. Our awareness itself becomes part of the process.
The act of paying attention, of asking a question, influences the system. That's why the double-slit experiment feels so unsettling. It shows us that reality does not unfold the same way whether we watch or not. Awareness, observation and measurement all merge into one. We aren't detached from the universe looking at it from a distance. We're participants woven into the fabric of the event. This becomes especially important in the world of quantum computing and modern experiments. Quantum computers rely on particles existing in superpositions holding multiple states at once. This fragile balance is what gives them their incredible potential power, but the very act of observing those states destroys the superposition, collapsing the particles into one outcome. In other words, the observer effect becomes the central obstacle to making quantum technology work. Scientists have to design systems that remain untouched long enough to process information, while still finding ways to extract results without breaking the quantum state too early. The same challenge shows up in delicate experiments across physics. Researchers must constantly ask, how do we measure without collapsing? How do we observe without interfering? These questions don't arise in classical science because in the macroscopic world disturbances are minor. But at the quantum level, observation itself is the disturbance, and avoiding it is nearly impossible. That's why so much effort goes into creating isolated environments, shielding particles from noise, and delaying measurement until the final moment. What this reveals is that the line between us and the universe isn't as sharp as we once thought. Every test, every observation, every attempt to look closer pulls us into the picture. The observer isn't outside of the system. The observer is part of it. And that truth changes not only how we see science but also how we understand our place in reality. Some thinkers take the observer effect to its most radical conclusion. The observer doesn't just witness the world, the observer creates it. According to this perspective, reality is not a fixed stage where events play out on their own. Instead, it is a canvas of possibilities that only takes form when someone looks. Without an observer, there is no definite world, only potential, only waves of probability. This view suggests that the very act of awareness is a creative force, shaping existence moment by moment. But not everyone agrees with such an extreme interpretation. Many scientists and philosophers argue that the world does exist independently of us. The mountains, the oceans, the stars, they're not waiting for us to open our eyes to become real. Instead, what observation does is filter, shape and collapse reality into something definite. It doesn't create the mountain, but it decides which version of the mountain we see, or how we interpret what that mountain is. In this view, reality is like a vast library filled with endless books. The observer doesn't write the library into existence but chooses which book is pulled from the shelf and read. This raises a fascinating question: are we co-creators of or are we interpreters of a world that already exists? If the observer truly creates, then consciousness plays a central role in bringing the universe into form. If the observer only filters, then our role is less about creation and more about collapsing infinite potential into a single experience. Either way, the observer cannot be dismissed as passive. Something about the act of watching, of measuring, of paying attention, is fundamental to how the universe unfolds. These ideas don't just stay in physics labs or philosophy classrooms, they touch on how we live our daily lives. If reality is an interpretation, then what we see, what we focus on, and what we give our energy to becomes the version of the world we experience. If reality is created, then we hold even more responsibility, because our awareness may be shaping the very fabric of existence. And if reality exists independently, then observation still matters, because it decides which face of reality we come to know. Each perspective points to the same truth: the observer is inseparable from the observed, and the world you encounter is never completely outside of you. A common misconception about the observer effect is that the conscious human mind alone collapses the quantum wave. This idea has been popularized in books, movies, and even some spiritual teachings, but it is not supported by mainstream physics. The collapse of the wave function doesn't require human awareness. Machines, detectors, or any kind of physical interaction with the system are enough to trigger the shift from probabilities into a definite outcome. The universe does not wait for human eyes to open before deciding what is real. Instead, it responds to interaction, to measurement, to contact. This is where it becomes important to separate the observer effect from other key ideas in quantum physics. Many people confuse the observer effect with Heisenberg's uncertainty principle. The uncertainty principle is not about observation creating reality. It simply states that there are fundamental limits to what we can know about certain properties of a particle. For example, if we measure a particle's exact position, we lose precision in knowing its momentum and vice versa. This is not a flaw in our tools, it is built into the fabric of nature. The observer effect, on the other hand, is about how measurement itself changes the state of the system, not just the limits of knowledge. Then there is decoherence, another concept that often gets mixed into the conversation. Decoherence explains how quantum systems lose their fragile superposition when they interact with the surrounding environment. A particle entangled in many possibilities can't stay that way once it bumps into air molecules, light, or other forms of noise. The environment effectively forces it to collapse into a definite state. This happens constantly in the macroscopic world, which is why we don't see large objects like cars or planets existing in multiple states at once. Decoherence is not the same as the observer effect, but the two are connected, because any act of observation is also an interaction with the environment. This leads to an important clarification. The observer effect does not mean that your thoughts alone can directly move planets, bend the laws of gravity, or make your car vanish. While it's tempting to link the power of consciousness to the mysteries of quantum physics, science does not support that. What collapses the wave is not human intention, but the physical act of measurement, whether done by a detector, a photon of light, or an interaction with the environment. Consciousness may still play a role in how we interpret and experience reality, but that is very different from claiming the mind alone rewrites the laws of physics. By making these distinctions clear, we avoid turning the observer effect into a kind of magical thinking. It remains mysterious, but it is not mystical in the way it is sometimes portrayed. The collapse of possibilities into a single reality is part of the structure of quantum mechanics, and understanding it requires us to respect the difference between observation uncertainty and environmental influence. Without this clarity, the observer effect becomes easy to misinterpret, stripped of its real power and depth. One of the most practical places the observer effect shows up is in quantum cryptography. In this field, secure communication depends on the principles of quantum mechanics. Information is encoded in the states of particles like photons. If someone tries to eavesdrop on the transmission, their very act of measuring the particles changes their state. The disturbance exposes the intrusion immediately, because the key no longer matches what was originally sent. In this way, the observer effect isn't a limitation, it becomes a powerful shield for security. It ensures that no one can secretly listen without leaving fingerprints behind. The system itself alerts both parties that an observation has taken place. The same principle, in a different form, shows up in computing. Programmers sometimes deal with what are called Heisenbugs, a play on Heisenberg's uncertainty principle. These are bugs in a program that disappear or change behavior when you try to observe them. For example, adding a debugging tool or inserting print statements alters the timing of the program just enough to make the bug vanish. The act of watching the system changes how it behaves. This can be deeply frustrating, but it perfectly illustrates the observer effect in technology. You can't always look at a process without influencing it. In psychology and social science, the observer effect has been recognized for decades. One famous example is the Hawthorne effect. In studies at a factory, researchers found that workers' productivity improved whenever they knew they were being watched. It didn't matter if lighting was brighter or dimmer, or if conditions changed in other ways. The key factor was awareness of observation. People's behavior shifted simply because attention was placed on them. This effect continues to show up in modern research, reminding scientists that their presence in a study can alter results in ways that have nothing to do with the actual variables being tested. Even in technology and engineering, this truth is unavoidable. When we build tools to measure delicate systems, those tools must be designed to interfere as little as possible. Whether it's a sensor placed inside a machine, a probe inside a circuit, or a camera recording an experiment, the challenge is always the same. How do you observe without altering what you are trying to capture? Perfectly non-invasive measurement is impossible, but technology constantly evolves to minimize the impact. Sensitive instruments are shielded, calibrated and refined to leave only the smallest trace. Still, some effect is always there. What ties all of these examples together is the same principle: the observer can never be completely invisible. From secure communication that relies on it, to debugging that struggles with it, to human behavior that responds to it, the observer effect is not just a quirk of quantum mechanics. It is a rule that runs through science, technology and daily life. Every attempt to observe is also an act of participation, leaving behind changes both subtle and profound. Our perception is never as neutral as we might like to think. From the moment we open our eyes, what we call seeing is already shaped by layers of interpretation. The brain doesn't just take in raw data, it processes, filters and adjusts based on memory, expectation and context. We believe we are looking at the world as it is, but in reality we are looking at the world as it appears to us through a lens we can't take off. This makes observation not a passive act but an active one, filled with influences we often don't recognize. Because of this, we never actually see a pure, untouched world. What we experience is always the collapsed version of reality that comes through the act of observing. Just as in quantum physics a particle's position only becomes definite when measured, our perception selects, limits, and finalizes possibilities into a single experience. In daily life, this plays out in how we notice some things and completely miss others. Two people can stand in the same room and report very different realities, not because the room itself changes but because the filter of observation collapses potential in different ways for each person. This idea challenges the assumption that there is a fixed reality waiting for us to view it clearly. Instead, what we call reality is entangled with the act of perception itself. We bring ourselves into the process, and in doing so we change what is revealed to us. Even something as simple as paying attention alters the outcome. If you watch a child playing, the child behaves differently than if they believe they are unobserved. If you study your own thoughts in meditation, the thoughts themselves shift because they are under the light of awareness. In both cases, the act of looking has reshaped what is being seen. Understanding this should invite humility. If our view is never fully neutral, then there may always be more present than what we can perceive. Hidden possibilities may exist just outside our chosen focus, waiting to be brought into form through observation. This is why discovery often feels surprising. We didn't create something entirely new, rather we revealed what was hidden until the moment attention turned toward it. The same is true in relationships, learning and personal growth. Potential is not always visible until the act of engaging with it brings it to the surface. The lesson here is not that our perception is flawed, but that it is partial. We cannot assume that the world we see is the world in its entirety. We see collapsed versions, simplified models shaped by attention, culture, memory, and context. Recognizing this frees us from believing too strongly in the limits of what appears. It opens the door to curiosity about what else might exist in the unobserved space, in the unseen layers of possibility that our perception has not yet drawn into form. So what is the observer really? Is it a conscious mind, a machine, or simply any device that interacts with reality? Physics has not yet given a final answer. What we know is that the very act of detecting, measuring, or becoming aware seems to play a role in shaping outcomes. That alone should leave us in awe. Can we design ways to observe more gently, with less disturbance, to let reality reveal itself more fully? Scientists are already searching for methods of passive observation, but the question remains, can such a thing truly exist? Or is every act of looking destined to leave a mark? Perhaps future physics will take us further, uniting observer and observed into a single framework. Some thinkers like Stephen Wolfram are already proposing bold ideas, visions of the universe where observation itself is woven into the very fabric of not as an add-on but as a core principle. If these approaches grow, they may change not just how we do science but how we see our place in the universe. The observer effect reminds us of something profound. Reality may not be separate from us. It may in some way include us. And that possibility alone changes everything. If this video opened your mind or sparked new curiosity, make sure to like this video and subscribe to our channel. There's so much more to uncover and your journey is only just beginning.